Hello students, welcome to this lecture on the carry look ahead adder. So up till now we had seen the carry ripple adder and then the carry skip adder previously, and then in this particular lecture we will take a look into the carry look ahead adder as well as just start or introduce you to the carry increment adder. Right, so let's begin with the carry look ahead adder. So let me also pick my pointer. Okay, so the carry look ahead adder, again, it is very similar to that of the carry skip adder. So the carry skip adder, we had this kind of an expression. To go through that, what it really means is we will make, if I have a 16 bits starting from 1 bit to 16 bit, we will make it into different groups here. And in this particular case, I have made 4 groups. And each of these groups, we will create, its own group generate. So G4 is to 1. And this one will have G8 is to 5. This one will have G12 is to 9. And then finally, this one will have G16 is to 13. So its individual subgroups or whatever the groups it has been formed, it will create its own group generate signals, and those group generate signals are created simultaneously. So basically for G16 is to 13, it doesn't have to wait for any of the previous group's output. And similarly, G12 is to 9 will be created simultaneously with respect to G8 is to 5, with respect to G4 is to 1. So all of them will be available, right? And then the moment the G0 is to 0 is fed, or it creates the G4 is to 0. So that's what is written here. G4 is to 0, this G4 is to 1 is created, P4 is to 1 is created, and then the moment G0 is to 0 is available, it creates G4 is to 0. And similarly, G4, whenever the G4 is to 0 is created, we will get G8 is to 0 if we have G8 is to 5 and then P8 is to 5. Right, so that's what the carry skip adder was doing. The additional carry skip adder does was it uses this particular expressions and then tries to deduce these expressions or implement this particular expressions in the form of a multiplexer. So it uses a multiplexer to skip some of the computation, and if based on the group propagate signals, it actually skips the other computation and just passes into the next carry out. Excuse me. So that's about the carry skip adder. So let's have a look at the carry look ahead adder. The carry look ahead adder, I have written the same expressions as that of the carry skip adder. Then what is actually the difference? Right, so it also utilizes the same, it makes it into the different groups of the bits, and then each of the groups are responsible to create its own group generate bits, and then the group or group propagate bits and group generate bits, so that to get the carry out of from that particular group. Right, so it is very similar expressions we will have, but we will see how it gets implemented. So let's take a look at the carry ripple adder. So if I write one particular expression for let's say G8 is to 0, it actually depends on so if I make G8 is to 0, so it actually depends on the second group generate bit. So it will be G8 is to 5 plus P8 is to 5 with respect to, and then if G4 is to 0 is available, then we will get this. So this was done in carry skip ahead adder or carry skip adder. In the carry ripple adder, if I want to get the G8 is to 0, so it has to depend on G8 is to 8 or the G8 bit plus P8 is to 8 or the P8 bit, and then it has to depend on the previous carry out coming from the 7th bit. Right, so if I write this in terms of the bit level, it will be G8 and then P8 and then G7 is to 0. So this was our carry ripple adder. Right, so the difference here is in the carry look ahead adder, it will be the same thing as that of the carry skip adder. So I'm going to write the same expressions here. P8 is to 5 and then G4 is to 0. So it also generates its own group generate signals and its own group propagate signals, and then it waits for the previous group's carry out signal. So this is very similar to the carry skip adder, but in the carry skip adder we had actually used a multiplexer, right? So if I write down the expression, so I'm going to use a different color. So G8 is to 0 was actually the output coming from the multiplexers, and then the multiplexer was something like this. The select line was the group propagate signal, and P8 is to 5. Right? This was actually the carry skip ahead adder, right? So I'm going to demarcate all this three so that we will get a clear-cut idea. So this is the first one is the carry skip adder, and then the second one is carry look ahead adder, and the third one is our regular carry ripple adder. So where the carry out gets rippled so that we'll be able to generate the next carry out. So the carry out keeps on rippling till the nth bit, the carry out from the nth bit is generated. Whereas in the carry skip adder, it uses a multiplexer. If the multiplexer, what it really means is if I have, so G8 is to 5 is already available, right? G12 is to 9 is already available. G16 is to 13 is already available. So the moment P8 is to 5, if it is not 1, not 1, right, then it is already available, and then it can directly, if it is not 1, that means if it is 0, then G8 is to 5 can be directly propagated as the carry out of G8 is to 0. Right, so that's the advantage the carry skip ahead, the skip adder has. Right, so again, so the G8 is to 0 is generated, but then again G12 is to 9, or rather P12 is to 9. If it is 0, then whatever it has created, G12 is to 9, it will be passed as the G12 is to 0. So it actually skips the evaluation of the carry out here. Right? It actually skips the evaluation of G8 is to 0. Need not have to compute, because if P12 is to 9 is 0, then whatever is computed here, G12 is to 9, it will be propagated as 12 is to 0 as a carry out. Right? So it doesn't have to wait at all. But if it is 1 here, then it has to wait for G4 is to 0 computation. Right? So that's the CSA. The CSA, the carry skip ahead adder, has an advantage if the group propagate bit is 0. Right? Whereas this carry look ahead adder, it doesn't use a multiplexers at all. So it uses, instead of deriving one inverter here and then putting it into a multiplexer, it directly uses the AND gate, here the AND gate, and then here the OR gate. So it uses the AND and OR gate. So it uses the AND and OR gate instead of the multiplexers. Right? So the advantage is, irrespective of the group propagate signals, it is going to generate the G8 is to 0. Right? So even if in this particular case, carry skip adder, if P8 is to 5 is 1, then it has to do the AND computation, and then that will be passed as G is to 8 is to 0. Right? And then the additional inverter delay is there for the P8 is to 5. Here, that additional inverter is taken off, and then it will do an OR operation. So it has to, this is anyways made available. So it will compute this P8 is to 5. This is also made available. So it will compute this AND operation and then do an OR operation and then get the carry out result, which is nothing but G8 is to 0. Right? So it doesn't have to wait, it doesn't have to do an inverter this thing. And so whatever is the, when P8 is to 5 here is 1, it has to do an AND operation and then pass it as the G8 is to 0. Right? So the passing through the multiplexers are generally done using the pass transistors, and then it will have its own delay. So in that sense, it is a much more simpler design, carry look ahead adder. And we say that it is looking ahead. The reason is very, very simple. So it doesn't really, the moment 4 is to 0 is generated, we will get 8 is to 0. The moment 8 is to 0 is generated, we will get 12 is to 0. The moment 12 is to 0 is generated, we will get 16 is to 0. So it actually looks ahead to the carry out of the next group without even trying to calculate the 7 is to 0 or 6 is to 0 or 5 is to 0. All right. Moving ahead. So the circuit or the block diagram of this particular subsystem adder system is nothing but two blocks here and here, which generates G4 is to 1, P4 is to 1 for the first group. The second group, it generates 8 is to 5, P8 is to 5. Very, very similar to that of the carry skip adder. Instead of the multiplexers here, it will do an AND and OR operation. So P8 is to 5 ANDed with that of G4 is to 0. And then OR with that of G8 is to 5, and then it generates G8 is to 0. So this is for only for the 8-bit addition. We can extend to 2 more blocks for a 16-bit addition. Right, remember that it ultimately it has to create the sum bits. Ultimately, it has to extract the sum bits, not only S8 or rather S9. G8 is to 0 will give us the S9 sum bit. But we also want the sum bits from S8, S7, 6, 5, 4, 3, 2, 1. Right? So what it really has to do is, internally in this particular adder, it has to generate G0 is to 0, G0 is to 0 is anyways made available, G1 is to 0, G2 is to 0, G3 is to 0, so that after the XOR operation here, it will give me S2, S3, S4, and then so on. Right? So we want all the sum bits, right, from 1 to 8. Right? So to generate the sum 1 to S8, we need all this, in the individual groups, group generate bits. Right? So even if I'm taking the 1 to 4 bit, this particular logic is anyways going to create 4 is to 0, but still I need a G3 is to 0, G2 is to 0, G1 is to 0, so that I should be able to calculate the other sum bits. So this block is going to do that. Going to extract the G3 is to 0, 2 is to 0, G1 is to 0. So the internal group generate signals, this particular block is going to do. Similarly here, this particular block is going to generate G7 is to 0, G6 is to 0, G5 is to 0. Right? And the way it does is in the PG architecture. So this is my PG architecture diagram. Alright, so the first stage is nothing but the bit-wise the generate and propagate signals. The second stage is the group-wise generate and propagate signals. The third one is nothing but implementing the XOR gate so as to extract the sum bits. Right, we are considering the G0 is to 0, or the carry input is nothing but grounded, so that is 0 logic. And notice here that all these blue boxes are generating its own group generate signals. So G4 is to 1 is created by this three the square blocks, which is nothing but each of these blocks is representing AND and OR gate. Right, so it is creating G4 is to 1, this one is creating G8 is to 5, 12 is to 9, 16 is to 13, and simultaneously it is also creating P4 is to 1. Right, so it is not only G4 is to 1 but also P4 is to 1. It is also P8 is to 1, 8 is to 5. This is also P12 is to 9. This is also P16 is to 13. So the output here is generating the group generate as well as the propagate signal. So once that is available, then it goes to the, instead of the multiplexers here, it will go into the AND and OR gate. So the red box is nothing but the bigger AND and OR gate, which takes in G4 is to 1, P4 is to 1, and then G0 is to 0, so as to generate 4 is to 0. Once the 4 is to 0 is generated, this is anyways made available along the same lines as when G4 is to 1 is the output generated. So G8 is to 5, 12 is to 9, 16 is to 13 is all generated at the same time. Right. So once we have that, that goes to the AND and OR gate. The other input is coming from 4 is to 0, and then the moment 4 is to 0 is created, it will try generating 8 is to 0. The moment 8 is to 0 is generated, we will get 12 is to 0. The moment 12 is to 0 is generated, we will get 16 is to 0. Right. So this way we will be able to generate or look ahead into the carry out of the individual subgroups here. So without even worrying about 7 is to 0, 6 is to 0, and 5 is to 0, which are actually useful for generating the some 8-bit, some 7-bit, and some 6th bit, without even actually generating this. It is actually generating 8 is to 0. So it is actually looking ahead. It is actually looking ahead to 16 is to 0. Without even considering, when the 15 is to 0, 14 is to 0, 13 is to 0 is generated. And that's why it is called as the carry look ahead adder. right? The other thing is, once we understood this three blue boxes here for all the subgroups, and then this particular red boxes to generate 16:0 for a 16-bit addition. This this three boxes, which is nothing but representing the and or gates, it is useful to generate 1:0, 2:0, 3:0. The moment 0:0 is made available. And similarly, the moment 4:0 is made available, it will, this particular block and an OR gate is going to generate 5:0. This is going to generate 6:0, 7:0. And similarly, 9:0, 10:0, and 12:0. Now remember that if I want to pick G7:0, right? G7:0 is actually created by G7:7 plus P7:7, and it has to wait for G6:0, right? So internally, this internally within that particular group, this is still a carry ripple addition. Only externally within, interaction between the four groups, it does utilize the carry look ahead adder, because here its own group generate and then propagate signals are created. But internally, when it generates the 3:0, 2:0, 1:0, or 7:0, 6:0, 5:0, it actually does the carry ripple addition. Right? Here also it is nothing but the carry ripple, so it actually waits for the previous one and then generates G4:1, G8:5, G12:9, 16:13. Right? So while it is interacting between the subgroups, we have an AND and OR gate, so that we will get directly the the 4:0, 8:0, 12:0, and 16:0. Right? Hope this is clear. So what should be the delay of this particular carry look ahead adder? So it will have a bitwise generation delay. It is nothing but an XOR gate and an AND gate, whichever one is higher, that will we have to account for. In the third stage, it will have an XOR gate delay. So that's what we have, the XOR gate, and then the PG represents the bitwise. This has to be bitwise. PG propagate and generate signals, and then it will have this three blue boxes here. The delay due to these three blue boxes, the delay of this particular box, this particular box, this particular box. And then finally, S16, if I am considering the 16-bit addition, we are really interested in finding out the delay for generating these 16-bit sum. Right? So in that sense, it will have the delay coming from these three particular blocks. So overall, I will have the critical path coming from these three blue boxes, these three red boxes, and then these three green boxes. Right, so we will have this delay from the three blue boxes, red boxes, and then the green boxes. So now what all these boxes are nothing but the AND and OR gate. So it is basically 3 AND and OR, 3 AND and OR, 3 AND and OR gates delay. So 3 AND and OR, 3 AND and OR here. And this particular blue boxes are written as nothing but PG of N. Right, so what it really means is it has been generalized into an N bits having K groups of N bit each, right? So N bits each. So in that sense, these three blue boxes, three blue boxes, these three blue boxes, three blue boxes can be generalized into the TPG of N here, where N here is actually nothing but the 4 bits, right? So it is basically generating the AND and OR gates at the output here. This is what the output here, whatever is the delay here, that is considered as TPG of N bits. So group wise propagate and generate signals for the N bits. Right, hope that is clear. So we will have the delay as nothing but 3 TAO, 3 TAO plus 3 TAO. So overall it will turn out to be 9 TAO. And when I compare this with that of the carry ripple adder, so we will have the same 3 TAO here, the same 3 TAO here. The only thing here will be the multiplexers. Right, so the carry ripple adder, the carry skip adder will have the multiplexers here. The advantage with the carry skip adder is because of the multiplexers, if the P4:1 or P8:5 or P12:9 or 16:13 is actually 0, right, then it will actually take its own generated signal and then pass it to the next one. Right, so if this propagate group of signals is 0, this is 0, this is 0, then it will directly generate, it will actually go really fast up till here, and then it has to do only the 3 addition. Right, so in that sense, it will be really faster. It doesn't have to wait for this signal to come, right, or rather this signal to be achieved. So it will be really fast to generate the output, but that will be one of the best case. In terms of the worst case, the P4:1 or the P8:5, P12:9, and P16:13 will be 1, and and then it has to wait for the previous carry out signals. And in that sense, I think the carry look ahead adder, because it's a simple AND and OR gate, doesn't involve any kind of an inverter to invert the group propagate signals, we will still have a better performance or a delay here from the carry look ahead adder. And that's why we say that the multiplexers consume a little bit more delay than that of a simple AND and OR gate. All right, hope this is clear to everyone. So the overall delay or overall critical path is denoted like this by this particular black line, indicating in this particular middle stage, the critical path or the maximum delay that it takes in this particular stage, and it is 3 blue boxes, 3 red boxes, and then 3 green boxes. So finally we have T XOR TPG is nothing but the bitwise, and then this TPG of n is nothing but the group generate and propagate signals, whatever is needed, and whatever is the delay due to those particular AND and OR gates. All right, hope this is clear. So for a general expression of k group and n bits, we will have TPG, and then TPG of for the n bits, which is nothing but n-1 TAO, and then we will have TAO as n-1 plus k-1 plus T XOR. So this k is k-1 decides the number of the big or the red boxes which we had, the AND and OR gates, which is going to interface between the different subgroups. And this n-1 is our last groups, the AND and OR gates, and then this particular TPG of n-1 is our first, first AND and OR gates, or the first groups AND and OR gates to generate the group propagate and generate signals. The XOR n will be nothing but for the last stage to extract the sum, and then this TPG, which is nothing but bitwise, is our whatever is the gates that has been involved, whether it's an XOR gate or an AND gate, whichever takes more, to create the bitwise generate and propagate signals, right? That will be there in the first stage, right? So hope this is clear. So let's move on to the carry increment adder. So carry look ahead adder and carry skip adder, the expressions were very similar, or rather it was derived from this particular expression. So if I notice this G8:0, it is actually created from this G8:5, P8:5, and then G4:0, right? But if I look into the other, the subsets of the carry out signals within the same group, the group of 8 to 4 bits, right? G5:0 is actually created from G5 plus, or rather OR with that of P5 and with that of G4:0. Right, G6:0 is nothing but G6 plus P6 and with that of G5. And G7:0 is actually created G7 plus P7 and G6:0. So if I look back into the my PG level diagram here for the carry look ahead, so I'm talking about this particular 3 gates here, 3 AND and OR gates, 3 AND and OR gates, 3 AND and OR gates here, right? So if I want to create the individual groups carry out and its subsequent the sum bits, for example 3:0, 2:0, or 1:0, or in this particular case 7:0, 6:0, and 5:0, then I need this kind of a carry ripple kind of an architecture here, right? Where carry ripple in the sense this one has to wait for G4:0 here, and then 5:0 is generated, and this has to wait for 6:0, and then this has to wait for 6:0, and then 7:0 is generated. So rather, if it's a very sequential flow. 7:0 has to depend on 6:0, 6:0 has to depend on 5:0. The question is, can we actually design it in the sense that once the 4:0 is available, why not all of them are made available? 7:0, 6:0, 5:0, just like how 8:0 is made available, right? So if I look into this particular expression of 8:0, 8:0 depends on this 4:0 and 8:5, G8:5 and P8:5. Now similarly, if I want to create the similar expression here, this block can actually be brought into the same level But I need not only 4 is to 0, but also I need 7 is to 5, P8 is P 7 is to 5. Here for generating 6 is to 0 at this level, I'll require G 6 is to 5 and P 6 is to 5. Right. So that's what the carry increment adder does here. So here, instead of waiting for G for 6 is to 0 to be generated in the 7 is to 0, or 6 is to 0 depends on 5 is to 0, and 5 is to 0 depends on 4 is to 0. Instead of that, why not consider this 7 is to 0 and 6 is to 0. 7 is to 0 actually depends on 4 is to 0, very, very similar to 8 is to 0. The way the 8 is to 0 is generated, it depends on 4 is to 0, and then 8 is to 5 and P8 is to 5. Similarly, if G4 is to 0 is generated, and if 7 is to 5 and P7 is to 5 is made available, then with the help of G4 is to 0, it should be able to generate 7 is to 0 at the same time as that of 8 is to 0. Right? And then 6 is to 0, it depends on 4 is to 0. It doesn't depend on 5 is to 0 now, and depends on fully on the 4 is to 0. And the moment, if it is because 6 is to 5 and P6 is to 5 is made available, the moment 4 is to 0 is made available, then we will get 6 is to 0 at the same time as that of 8 is to 0. Right? And 5 is to 0 is anyways depends on 4 is to 0, and then 5 is to 5 and P5 is to 5. So if I look into the carry increment adder here, these two particular are changing. These two are changing with respect to this two. Right? All other two things remains the same. The carry out of the lower LSB side and then the carry out of the MSB side. In between the bits G7 is to 0, 6 is to 0, it is being generated at the same time. Right? So the moment G4 is to 0 is made available here. Right? Is made available here. All these things are created, and it is waiting for G4 is to 0 is to be generated, and the moment G4 is to 0 is generated, all these 4 bits, all these 4 group generate bits will be generated simultaneously. Right? So in a sense, each of this group, right? Each of this group 4 is to 0, 4 is to 1, 8 is to 5, 12 is to 9, and then 16 is to 13. All this group is actually waiting for the carry out. The moment that the carry out of the previous subgroups is generated, it gets incremented. Right? It gets holistically, all the groups gets incremented into the group generate carry out bits. Right? So that's why it is called as a carry increment adder. So it is waiting for one particular G4 is to 0, and so that in the next instance we will get the G8 is to 0 to G5 is to 0. All of them will be in the next increment of the instance, we will get all these carry out signals. Right. So the block diagram is pretty simple. You will have 4 groups here. This particular first group is 4 is to 1, and then this one is 8 is to 5, 12 is to 9, 16 is to 13. The first group, even if it does the carry ripple adder here, right, it is going to generate G4 is to 0. The moment G4 is to 0 is generated, we will have G 8 is to 0 that has been generated, but also G7 is to 0, 6 is to 0, 5 is to 0. The moment G8 is to 0 is generated, we will have 12 is to 0, but also we will have 11 is to 0, 10 is to 0, 9 is to 0. The moment 12 is to 0 is generated, we will have 16 is to 0, but also we will have 15 is to 0, 14 and 13 is to 0. Right, which will help in extracting this sum bits. Right, so the PT architecture here for the carry increment adder will look like something like this. A carry ripple addition here in the first block. The moment G4 is to 0 is generated, then it goes. Whereas while this particular 4 blocks is generating G4 is to 0, at the same time we will have 16 is to 13 being generated. This one is 12 is to 9 being generated. G8 is to 5 being generated. But not only along the outermost bit, but also on, inside this particular bit, we will have G6 is to 5. We will have G7 is to 5. And not only G7 is to 5 or G6 is to 5, but we will also have P6 is to 5 generated, and P7 is to 5 generated, and P8 is to 5 generated. So similarly here, when it is generating this one, it will be nothing but 10 is to 9, comma P10 is to 9. And then similarly here, G11 is to 9 and then P11 is to 9. So the moment G4 is to 0 is generated, I need one particular AND gate and an OR gate here, which is represented by a block, so as to get my G8 is to 0, 7 is to 0, 6 is to 0, and then 5 is to 0 simultaneously generated. So it is generated at the same time instant. So it gets actually, from G4 is to 0, it gets incremented to 8 is to 0, 7 is to 0, 6 is to 0, and 5 is to 0 at the same instance. And once 8 is to 0 is made available, then it will get 12 is to 0, 11 is to 0, 10 is to 0, and 9 is to 0 incremented. The moment 12 is to 0 is made available, then it will get 16 is to 0, 15 is to 0, 14 is to 0, and then 13 is to 0. Right? So in the sense, the 4 groups which are being created, it is actually once the G4 is to 0 is generated, then 8 is to 0 and all the other groups will be incremented in the next time instance. And then this will also be available in the next incremental time instance, and then this will be available in the next incremental time instance. So that's why it is called as a carry increment adder. And once we have this G16, in the individual carry out bits, then I should be able to generate the S16 to S1 bits, right? So the critical path in this particular case will be nothing but the S16 bit, how much amount of time it takes to generate the S16 bit, and it will be nothing but coming from this particular AND and OR gate, and this the input here depends on this particular AND and OR gate, and then that depends on this particular AND and OR gate, this particular AND and OR gate. So I will have this 4 AND and OR gates plus this one, and then finally this one. Right, so looking at it, it makes it very, very simpler. In fact, this is one of the most, the fast adder that we can develop, the carry increment adder, because the overall delay, it turns out to be 4 TAO and 3 TAO to generate the G15 is to 0, and then 1 XOR to generate the S16 bit, and then one the TPG at the bit level, PG at the bit level. So that will be the delay.